we're gonna Okay, so for today's session, the Friday, the 3rd of September, we're gonna continue our lecture since yesterday. Let's see, I'm gonna start share screen here and then let's check. So see, I have opened some of them. It's quite a lot, yeah, from module 2, segment 1 up to maybe around 4 or 5. So we're gonna learn a lot today. There is no assignment for today or quiz, no, but please listen if you have any questions. I can start to pause and then explain to you. Okay, so here, I think we started here, yeah? Should be here, okay. There, let me check if I put it full screen. Right. Okay, so again, this is the design problem. This is a distillation column. You have the feed, you have the distillate, you have the bottom. Can you see my screen in full screen?
Yes,
Okay, good. Right, and what we're gonna do is we're gonna do this one, yeah, the process design. Okay, so usually for problem solving is for master. So now we're gonna start to learn about the process design. How to, if we have some feed, for example, 50% of A, and we want maybe 95% of A, and how much the stages that we have to calculate. Right. And then, so yesterday, we also talked about the total and component mass balance. Yeah, just to refresh us again from yesterday lecture. If we make this envelope, and this is the feed, so the input equal to the output, which is the feed equal to distillate and bottom, right? Okay, and then check again the component balance. So if we have, let me show you here. If we have two component A and B, so this is the Z is the molar fraction of A in the feed. Yeah, so A in the feed. Okay, and then this is for example X distillate. Yeah, X distillate of A. So for example, 95% of A, and also bottom of A. Okay, so then this is so for one particular component for A, so ZF of A multiply with the feed, this one, yeah, multiply with the feed would be equal to X in the distillate of in the A multiply with the distillate and plus the XB of A in the bottom. Okay, so this is your total and component mass balance. Okay, and then we also have defined the pressure condition. So usually how we define the pressure condition always correlated with the condenser, because we have to condense the vapor, yeah, from the top stage, from the stage 1. Okay, but there are two type of condenser. There is a total. This one is total. Why is total? Because the vapor we condense them, all of them become liquid. So this is a total condenser. Yeah, but for later on, so the total condenser, if we have the feed, okay, this is full of become liquid. Yeah, from vapor become liquid. Another one, so this is total condenser. Another one is called partial condenser. In partial condenser, you have one feed, yeah, when you vaporize them, it's not sorry, okay, it's not really full into liquid, but then you like some sort of flash them, it become vapor and also liquid. So this is, and then yeah, and this is called a partial condenser. Later we're gonna learn about that as well. Right, so let's just continue again, and then also the divining temperature. If we okay, so this one there, check this, okay, oops. So if the TF is the temperature composition, yeah, of the feed, and then the phase of the product is known. So by using the TXY diagram, we can determine the appropriate product temperature. For example, a feed is around here, yeah, and then we want the outcome is the distillate, for example. Okay, if the distillate is if we take the distillate as a liquid, then when you know the composition of the liquid, let's say I want to get 95% of liquid of 0.95, the composition of 95% of A in the liquid phase. So that means your temperature of distillate is here, yeah, okay, because this is the liquid line, okay, the liquidus line, okay, the liquid line, yeah, this is vapor and this is liquid, saturated liquid line. But if you collect the distillate in vapor, then that is your temperature of vapor, okay. Okay, so then let's next. Now, okay, now we start to learn about fractionation. It's called top section or enrichment or rectifying section. So this is a sketch of fractionation column. This one is stage 1. Please delete this one, yeah. So this one chamber is one stage. Okay. Number 2, it's number 3, number 4. Okay, and this is N maybe, and this one is where is the feed. So when is this is the feed, so this is N plus 1. Okay, again there's something wrong here. Oops. Okay, yeah, the N plus 1. So I would like to ask, can you I'm gonna maybe I will leave the sorry. I'm gonna leave the this one, the full screen, so I can maybe I can write better, because when it is full screen it's a little bit something wrong, yeah. Okay, let me check. Okay, I have if you see in the screen, I have activate annotation, so you can also contribute to us, yeah. You can also draw something in the screen. Okay, so this is there's an annotation. Can you see annotate on the screen? Hello, in your Zoom screen there is annotate.
Yes.
Okay.
Which one? Yang mana?
Ini you're viewing Winnie Wulandari's screen, and then there's the view option. Click that, and then there's annotate.
Oh, okay.
Yeah, okay. So you can draw it with your cursor or something with mouse, yeah. Or if you have a pen, then you also can have a pen. Okay. Okay. Let's make it bigger so I can. Okay. Now I would like to ask who I can ask. Fatia, are you there?
Hi, Miss. I'm
Okay.
here.
Can you show me which one is the condenser? Can you write something or make a circle or something? Where is the condenser?
Is it the top? Wait, let me try to annotate. Can you see my pen?
Nope. Oh yeah,
Oh,
you can. Yeah, I can.
is it this one, Miss? This one?
Yep. Get.
Uh, yeah, this one.
Okay. Next question. What is the product of the distillation column? Is it in
Yep.
liquid or in vapor?
It's in vapor, and then it goes to the condenser, and then it becomes liquid.
Okay, so you should as the product of distillation is the liquid. Yeah, because this is the product. Okay, so this is not the product. Yeah, okay, it is vapor and then your liquid. Okay, I would like to ask Ilham. Ilham, are you there?
Yes, Bu.
Okay, Ilham, can you show me which one is the tray number one, the chamber number one?
How do I annotate again? Oh,
Check the.
tray number 1. Is it this one?
Yes, good. Okay, yeah, good, Ilham. That's right. Okay. So, Alisa, are you there?
Yes, ma'am.
Okay, Alisa, do you know what tray is it when the feed goes into the distillation column? Which
I
one?
think this one, ma'am.
Yes, this one. That's right. Your green things there. And then what is the name? How do you say that? Tray berapa? So this one is tray n+1 ya, Alisa. Okay. So this
Okay,
is
ma'am.
tray n+1. Okay. Right. Okay. Good. Okay. Thank you everyone for your participation. So next, let's continue to hear the top section. So the analysis of enrichment section, including the condenser. The enrichment section has n theoretical stages. Yeah, n theoretical stages, but usually it includes the feed. So it should be actually. So I'm gonna draw it here. Let's say it should be n+1. Why? Because it is including the feed. Yeah, this is including the feed. See, I write better in here. Okay, so here, what is the enriching section for? Yeah, it has n. Actually, we calculated n, but it should be including the feed. So I think we have to put the feed over here. Yeah, so it becomes the n. Maybe feed over here. Right. Okay, and also it's including distillation, including condenser. If later on we're gonna learn if the condenser is in equilibrium. Okay, in this case, is it the condenser is in equilibrium? Dhamma, do you think in the condenser only, yeah, is it equilibrium or not? What do you think? It's only condensing from vapor to liquid, so is it equilibrium or not? I don't think so, yeah, Dhamma, yeah, because we only condense it. If you condense it, there is no equilibrium on the condenser. But if I have another condenser, which is called, I would call partial condenser like this, so I vaporized some of them, but then and also I got the liquid, but sorry, I need to delete this. Okay, okay, but I take the product as a vapor again, yeah, as a distillate. This one, okay. So I got the product as a vapor and the reflux as a liquid. This one is very. This is when you learn in thermodynamics about flashing, yeah, about flashing when you maybe change the condition and then some of them become of liquid and vapor and then some of them become liquid. So this one is this one is equilibrium or not? Dhamma, what do you think? There is a vapor and liquid in the condenser. So is it equilibrium or not? One stage of equilibrium or not? Anyone? Fatia?
I think it is, Miss.
Right.
It
So
is
that's right, Fatia. So because in if we call this is a partial condenser, yeah. If you have partial condenser, when just some of you put it into the liquid while we got the product as a vapor, this is a one stage equilibrium. So then you have to calculate the one stage is from condenser. Okay, but if you use a total condenser, this is not equilibrium because you only condense vapor into the liquid. So this is your number 1. Okay, I'm gonna go back here again because in the exam, okay, I can start to use kisi-kisi ya dari sekarang. Usually there are two type of questions for the condenser. First is the total condenser. The second one is partial condenser. If it is a total condenser, then you didn't put number 1 in here. Yeah, you'll put 0 in here. So number 1 is in your first tray. Yeah, like Ilham said, this is tray number 1. But if you use a partial condenser, this is gonna be your stage 1. Okay, got it, everyone? Okay, I'm gonna go back here if you still got confused. Yeah, that's fine. Okay, so let's go to the next slide. Right. So how to know the amount of vapor and amount of liquid? Yeah, in here. Then maybe we can. So I'm gonna erase this one. Which one? Okay. Anyway. So again, we gonna write the total mass balance. Yeah, the total mass balance is very important. So for the enrichment section in the mass balance, let's look at the total mass balance, but from this envelope. Okay, from this envelope. Okay, from this envelope. Okay, so let's first look at the one that leaving. The one that going down, and also the one that leaving. Yeah, when the stream that's going inside here, one is the Vn plus 1. Yeah, can you see it? Okay, okay, and then the one that goes out is this one, Ln. This one is D. Okay, so Vn plus 1 is the vapor that goes into N plus 1. That goes from N plus 1. That leaving tray N plus 1. Okay, so the name. Always the name, always for vapor, it's always leaving the tray. But for liquid, it is always going to the tray. Yang vapor itu pasti selalu meninggalkan tray, yang liquid itu pasti selalu masuk ke dalam tray. That's how we name it, ya, cara penamaannya. Right? So for example, this one, this is tray N. So this is Ln, which is the amount of liquid that leaving tray N. Okay, this one is Vn, yeah, this side. because this is the vapor that leaving the Vn, the tray n. So the purple one here is called Vn plus 1 because it is leaving the tray n plus 1. Okay, so now let's look at the mass balance. Vn plus 1, this one that goes inside, equal to Ln plus D, right? Okay, so good. So you have a total mass balance. Okay. The second one, we have to calculate also the component A mass balance. Yeah. Yn plus 1 is the mole fraction of vapor leaving n plus 1. So Yn plus 1 mole fraction of vapor leaving tray n plus 1. Okay, yeah. How about this one, xn? Can you help me? What is xn? Maybe Dia, are you there, Dia? What is xn? Mole fraction of vapor of vapor or liquid? Or X?
I think it is liquid.
Yeah, that's good, Dia. So mole fraction A of liquid, yeah, because component A mass balance, yeah. Is it leaving tray what? Tray n or tray n plus 1 or n minus 1? Yeah.
I think it is from tray n.
Yeah, that's good. Okay, let's just write it here, yeah, of course, because this is your first time to read this one. It takes a while. Okay, yeah. So if you check the component mass balance, Yn plus 1 multiply with Vn plus 1, this one, equal to xnln plus xd multiply with the mole fraction, molar flow of distillate. Okay, so then we get that one. And then let's divide them both sides with Vn plus 1, both of them. Okay, so this one it cancel out, Yn plus 1, and then you end up with Ln divided by Vn plus 1, xn plus xd d divided by Vn plus 1. Okay, so this is a number, yeah, Ln is a number because you know the flow, okay, for example 100, yeah, okay, V also a number, okay, and then xn is a variable, and also y also also change with Yn plus 1 change with xn. Okay, so we can have for example, if this is x2, then we can get y3, yeah, and so on. Okay, so this is equation, persamaan, yeah, and it is looks nice, the equation, and it is also a linear equation, yeah. Can you see? So this is because it looks like y equal to mx plus a constant here, so it looks like a linear equation, yeah, persamaan linear. So that means if I know the value of this one, I know the value of this one, if I know that one, okay, so that means I can, if I have one xn, for example, I can get the Yn plus 1, okay. So that is this is called the operating line later on. Okay, so let's going to the next stage. Okay, so in McCabe-Thiele approach, this is in the book, yeah, from the McCabe or the Treibold, yeah, we use the tray ball books. Let me check. Yeah, I have. We have a tray ball book. So this is quite old book, tray ball. This one, yeah, the mass transfer operation. Maybe you can find the scanned somewhere. Let me check the. Ilham, maybe can you delete your annotation now? Ilham? Okay, thank you. Okay, let's go back. So I just want to show you that because we really got it from the where is it? Check the so the mass transfer gas liquid operation, liquid solid fluid, gas liquid distillation 342. Yeah, this one. Yeah, so this is the distillation, and then let's check. So we're gonna it's multi-component and then binary mixture, volatile reactivity. This one also, yeah, that we just looking at. Yeah. Yeah, this is about enriching section. Yeah, we call it McCap-Thiel. Yeah, this one. So there is a very old paper but very rigorous, and then it quite valid. Yeah, so we use the McCap-Thiel method. Okay, see, there's a lot of books. So okay, so let's go back to here. Let's start to check it again. Number. Okay, yeah, this one. Okay, so that's using McCap-Thiel's approach. So in the McCap-Thiel's approach, we approach a constant molar overflow. So we assume that because they is actually in contact, and then it's leaving out those stages, and then it's in contact again, and then leaving out those stages. So the amount of vapor and liquid is not really changing. Yeah, it's not changing. So then we assume that it is a constant molar overflow. Okay, so then we assume that V1, V1, V2, V3, and then so on is actually V. Okay, because there's nothing here. Yeah, because there's no changing there is no drawing, or there is no input coming in, and then so we call it constant. The liquid also, we assume that it is a constant molar flow. So if we go back to the previous equation, yeah, you can also maybe, if you can write it, maybe you can start. So this the Vn plus 1 n plus Vn plus 1 also Ln. So usually we can just diminish the number here, yeah, the index here. So that becomes, go back here, okay, L, yeah, the liquid is for the L, and V is for the vapor. Okay, so that means yn plus 1 equal to L over V xn plus xd multiply d divided by V. Yeah, So this is constant, this is constant, this is constant, this is constant. So it's resulted in operating line x versus y, and the equation is linear. Yeah, y equal to lvxn plus xd. Yeah, so this is this one is what is called, this is gradient. Yeah, and this one is a constant. Okay, so that means if I because why we have to do this operation line, because we want to know all the composition inside. Yeah, okay. In order to we know the L and also the V, we have to know which one that goes back into the fractionation column. Okay, we have to know the L. Okay, because like Fatia said in the beginning, there is for example, it is not a equilibrium stage. Yeah, and if we see mass balance, let's see this envelope. Yeah, that's this envelope. In the envelope, we know that the mass balance V actually okay, V equal to L plus D. Yeah, okay, right. And then we introduce R, or reflux ratio. Yeah, the reflux ratio is the amount that goes inside divided by the one that goes outside the fractionation column. Okay, if you have high reflux ratio, so that means most of your liquid going back into the distillation column, and then you get less distillate. Okay, if you have a very low reflux ratio, so that means you get a lot of distillate, but you don't have a small liquid coming in. Okay, remember, we need the liquid coming in because it has to counteract with the V. Yeah, and then we need the L also in the equation before. Okay, so let's go back to here. So V equal to L plus D, and then let's divide both sides with D. So let's divide both sides with D. Okay, so then V divided by D equal to L divided by D plus D divided by D. Okay, yeah, and so we know that L over D is a reflux ratio. L divided by D is a reflux ratio. Okay, yeah, so we can get that V over D actually equal to reflux ratio plus D divided by D 1. Yeah, that is much easier because in the control process, in the distillation column control process, we can just adjust the valve, and then also to regulate the reflux ratio, make it bigger or make it smaller. Okay, so then we have this this equation. Okay, and then let's go back to the equation back here. So it is y n plus 1 equal to L divided by V xn plus x d divided by V. See, so this is in here there is L over V. There is D over V. So I'm gonna write it here. So just to make it easier to put everything back here. So y n plus 1 equal to L over V xn plus xd multiply with D over V. Yeah. Okay, so let's change this equation with something with reflux ratio here. Okay. So then also we have to know here L over V. So okay, so we have to know also, so we know V over D is there, or well, here is D over V. So then we can get here that D over V is 1 over R plus 1. Yeah. Okay, so we can change it here. Okay. Yeah. The next one, also using this equation, we can also find V divide L over V, yeah, L over V here. We also have to find L over V from here. L over V, while the R is L over D here. Okay, so so here we can get, for example, by substituting V L plus D into the R. Maybe let's try this one, because we want to know L over V. So maybe let's divide, go back here, V equal to L plus D, while R equal to V equal to, so L is equal to R L equal to R D, yeah, plus D. Oh yeah, this one is V plus D, yeah, sorry, I'm gonna put it back. Okay, so anyway, okay, let's try to do the derivation later, but if you want to know L over V, so we can try to find the L divided V, it becomes R divided by R per this one, yeah. So for example, if V equal to L plus D, and then divide them both of sides with divide all of them with D, for example, okay, and then V divided by D equal to this one, yeah, R plus 1. This one is right. Okay, and then with that one, find to L from this one here. Yeah, try to find L equal to V minus D. Okay, and then you can find the L, yeah, and then you can get L divided by V equal to R plus delta R, yeah. Yeah, we need to do some calculation to get this one, yeah. Anyway, after that we do this calculation, we will get that V divided by D is R plus 1, which is this one, and we will also get R divided V equal to R plus divided by R plus 1, which is this one. Okay, there. Okay, so then we can go back and then change this equation. So y n plus 1, we can change L over V with this one, R divided by R plus 1 xn, plus this one xd is just the same. D over V, we can change it with this one, 1 over R plus 1. So we can R plus 1. Okay, so then we get new equation that so we don't need to calculate which one L, V, and D, but we can just put it using reflux ratio, yeah, in both sides. So reflux ratio. Okay, so this is the importance of reflux ratio. Okay, So then we end up with this one. Yeah, so this one is called the top section operating line equation. Yeah, you have to remember the top section operating line equation is this equation. And what is the purpose of this top operating equation? In top operating line equation, you can, so if it is a tray number n, and then you have this one is x n, this one is y n plus 1, yeah, that goes inside. You can have the correlation, yeah. So correlation between y n 1 and x n in the tray n. So that means if you know the composition of the liquid that leaving out the tray, you can predict what is the vapor that goes inside the tray. Okay, this is the top operating line. Okay, now,
Bu,
yeah, okay,
I want to confirm something, Bu,
yes.
about yang yn plus 1 and xn. Are
Hmm.
they living from the same tree or not, Bu?
No. Good question. Is it Kevin?
Yes, Bu.
Okay. Now, Kevin, now I want to ask more question. So thanks for asking. So, Kevin, so what is the vapor that leaving the tray n? Which one?
Sorry, Bu, vapor?
Yeah, vapor that leaving tray n.
The vapor that is leaving tree n, then it's
So this one, yeah?
vapor, yeah, yn ya, Bu.
Yeah, that's right.
Vapor yn, right?
Maybe let's put this one, yeah. Maybe let's just put this one. Yes, good. So the one that goes inside the tray n is yn plus 1, but the one that leaving tray n is the yn. Good. Now, this is a very good question. Okay, so okay, Bu, we know the top operating section, this one relationship. But now, how to get the yn? Yeah, how to get the yn? This one, the green one. What is the correlation between yn and xn? Okay. Who want to ask? Gamma, are you there? Nadifa? What is the correlation between yn and xn? Yn, the vapor leaving tray n. Xn is the liquid leaving tray n. Anyone? Let's make me a hint from maybe
Bu,
yeah. Okay.
if I'm not mistaken, like when I see the reactor before,
yeah,
in 3n, yn is leaving 3n, right? However, the liquid is xn minus 1 that is leaving 3n. Is that right, Bu?
Which one? Sorry. Which one?
So the components that are leaving 3n, nah, like this one, Bu.
Yeah.
For example.
Fine. Okay. So for example, n, yeah. So the component that leaving 3n is this one, yeah. Yn and also xn. Yeah, right. Now, the question is here. Go back to maybe make it blue. We know the correlation between yn plus 1 and xn, okay, by the operating line, isn't it?
Yes, Bu.
Ya, tadi ya, y n plus 1 equal to r divided by r plus 1 xn plus x d divided by r plus 1. We know that. Now, I would like to ask, what is correlation between xn and yn?
Ibu, is it the equilibrium?
Okay, what's your name? Sorry?
Nadifa, Bu, Aska.
Nadifa, yeah, that's right, Nadifa. Yeah, that the correlation between xn and yn is like equilibrium. Okay, remember from my lecture maybe few yesterday. Is it in here? Let's go back to. From the thing, the top stages here. Is it or this? Okay, let's go back. Is it this one? Oh no, not this one, the previous one. This one. What happened in equilibrium? Yeah, what happened is in one stage. Yeah, the function of stages is first it contact between the vapor stream from the bottom and the liquid stream from the top. Okay, so then if you want to calculate it again like this, so okay, so this is the contact between the vapor stream from the bottom, which is yn plus 1, yeah, that we just discussed, and also the liquid from the top, which is we have the liquid from the top. Maybe this gonna be xn minus 1. Okay, and it will have a contact we call cross diffusion. You mix them together. If you shake them in a jar between the gas and between the vapor and also the liquid, yeah, or it can swirl around, make froth, yeah, berbusa, berbubbles gitu ya, to make diffusion. So they will contact with each other between the vapor and also the liquid, and then until it goes to equilibrium. So that's right, Navdifa. And then after it goes equilibrium, and then we have to separate them again. This one becomes yn, and this one becomes xn. Okay, yeah. So that's correct, Nadifa, and also to ask for Kevin. So yeah, that's right. Yn plus 1 is going inside the tri-n, and yn is leaving the tri-n. Okay, good. Let's go back to the which one is I need to
Excuse me, miss. We can't hear you. I think you're muted.
Sorry, I'm okay. Let's. I want to check to you first before about the. Wait. The material about maybe from last year's. About what happened in what is the distillation looks like, yeah, the distillation columns looks like, just to make sure. Segment, a lot of them. Perbandingan first. This one. So you get an idea what happens inside the tray column. So this is actually the tray column looks like, yeah. This is still few weeks ahead, but this is what happened in the tray column looks like. So this one is one tray, yeah. This is okay. So if I can draw it here, so this is tray N, yeah. This is tray N. This one is the which one? This one is the, what is this? Is this YN? Yeah, this one is the vapor that leaving the tray. So this is called YN. Yeah. So the one LN minus one, the tray from the liquid that came from another tray is called LN minus one. So they just gonna go down there, yeah, and then turun ke bawah, ya, goes to here, and then from down there is a lot of vapor also, yn plus 1. Okay, so Ln minus 1 and n plus, yn plus 1, the vapor from the preceded tray and also liquid from the top side there, they're gonna meet over here, and then they're gonna mix them together, okay, because it is fast. They're gonna mix them together to make a froth and also a spray, and mix them together. So after that it's very fast, and then it goes equilibrium, and the one that equilibrium with the equilibrium composition will leave the tray. So this is the L X, yeah. XN. So this is the XN and this is the YN. Okay, so that is the idea, yeah, the design, what happened in one tray. So this one is one tray, and again the XN goes to here. For example, this is n plus 1, okay, and then it's gonna leave out with over here usually, yeah. So that is the path, goes that one. This is become Ln plus 1, while we have maybe y n plus 2 maybe, yeah, from here. Okay, so a vapor coming in again, and yes, it's the one. Okay, so that is that. Just want to show you that is the one stage mean, yeah. So the one stage means that the efficiency 100% if all 100% can contact with each other and then leaving the equilibrium. But sometimes later on we're gonna learn that the efficiency won't be 100%, of course. Sometimes 80%, sometimes 70%. So it's gonna change the number of tray. Okay. Now I'm gonna go back again to the segment 2. So if we do the schematic, it would be looks like this. So this is the equilibrium stage. So if we know the xn minus 1, we can calculate yn by using enriching operation. Yeah, the enriching operating line, we can get operating line here. Okay, using the yn plus 1 equal to r divided r plus 1 xn plus xd over r plus 1. Okay, we know the distillate that we want, yeah, the outcome that we want, the outcome that we want, 99%, 95%. We will also determine the reflux ratio, yeah. Okay, the operator, please set the reflux ratio at this number. Okay, so we know the number here, we know the number here, we know the number here. So once we know the n, we can get the yn. Okay, and also here if we got the xn minus 1, we got the yn. For the equilibrium calculation, if we know the yn, we can get the xn from the equilibrium. Okay, so then usually we put it into a graph. Now we can start drawing the graph. And if you remember, for equilibrium correlation, first we have this diagram. If you remember, what is this diagram? TXY diagram, remember?
Yes, Bu.
Yeah, okay. This TXY diagram, in one such temperature, we can get a pair between the vapor and the liquid. Yeah, the liquid is called X, the vapor is called Y. Okay, so if we put this line into this graph, then you can get 1 point. Yeah, for example here, if you have a composition of X for the liquid there, yeah, we also and then this is the composition of vapor. Yeah, so this one particle point represent one line in the TXY diagram. Okay, so this is very important because sometimes in the exam you only got this this graph, yeah, TXY diagram, and in the exam you have to construct the XY diagram. Okay, so I think we're gonna put some assignment how to change the TXY diagram into XY diagram. Right, okay. So this is the equilibrium correlation. If this is xn, for example, so that is the yn. Yeah, so that is the equilibrium correlation, which is we don't have the equation here, but that's fine because we can use the graph, because it is only two component, but for maybe 3 or 4 component we have to use equation later. Okay, the operating line also because it looks like a line, so then we also can get correlation between yn plus 1 and also xn, and this correlation, yeah, because it is y equal to mx plus c, so it looks like a linear equation. We can put it in here. Okay, so let's put those equation, the operating line equation, into the xy correlation. So next step, okay, so then let's put it there. Okay, so the next step is to maybe let's move it. Sorry, let's move this somewhere first. Okay, first one, yeah, before, okay, before I put it there. Okay, first, if you have this equation y equal to mx plus c, what is your intercept?
C, Bu.
C, which is xd divided by r plus 1. Yeah, so you have to calculate xd divided by r plus 1, like this point here. So this is gonna be your intercept. Okay, and then another one, we can get the intercept, make a point. So first calculate xd divided by r plus 1. Okay, so this is, okay. The second one, we have to, because we want to make a line, yeah, we want to make a line. Rather than calculate the r minus r divided by r plus 1 here, we can also find the other point there. Yeah, put xd into equation. Let's say, yeah, x as xd. Yeah, so y equal to r divided by r plus 1 xd plus xd divide r plus 1. Yeah, r 1, yeah, 1 times xd, so equal to r plus 1 divided by r plus 1 xd, which is x1. Okay, so that means if the x is xd, y is also the similar number, xd. This line is a line of y equal to x. Yeah, so that means it should be in this line. Get it? So then you have two points. First is the intercept. The second one is this one, the xd comma xd, which is when the x equal to xd, your line, operating line would be on this one. Okay, so the next step is you can now put the line over here. Ta-da! Okay. Oops. Okay, looks like that. Okay, so that means you have the line. So you have operating line and you also have the enriching line. You have the equilibrium curve and also operating line. Okay, so that's why the operating line is through point xd and xd here. It is the explanation. And also the intercept at x equal to 0 here is xd plus 1, which is got, and then we can draw it. And those slope is r divided by r plus 1. Okay, so that is the construction. Okay, so that means now how to calculate the number of enriching stages. Yeah, how to calculate the number of enriching stages. I think I have to maybe put it there somewhere. Yeah. Okay, here's the thing. Yeah, please look at the schematic when I try to explain which points in here. Okay, yeah, so we have, okay, please, where's everyone? I need to, maybe I can ask you. Okay, yeah. Okay, Helena, are you there? Helena?
Yes, ma'am.
Yeah. Okay, Helena, what is the mole fraction of the distillate? Mole fraction of the distillate. First, the distillate is liquid or vapor? The distillate.
The distillate is liquid.
Yes, okay. What is the mole fraction of the distillate?
Is it the XD?
Yeah, this one. This is XD. Okay. And because this is, there is no, is this total condenser or partial condenser? Is there
Total, I think.
total, yeah, total, because there is no equilibrium. Good. So we can say also this is equal to x0, yeah, because there is no yeah, x0, which is it's not x1. Okay, good. Thank you, Helena. Dia, so when we have this one, the X1, yeah, for so what is the composition of the vapor? Is it the same from here to here, the liquid and the vapor?
The liquid inlet or outlet, ma'am?
The outlet.
I think is it the same?
Yeah. Just wait. Maybe I make okay. This one, yeah. So let's look at this line. Oops, a little bit down there. Okay. Okay. So this is the XD. Yeah. This one here, but when we have okay, so this is the XD in the vapor. When we cool it, when we the vapor actually, yeah. So what is so we know the XD, yeah, this one there, yeah. So what is the composition of Y1? Sorry, go back again, yeah. What is the composition of Y1? So the composition of Y1, okay, is actually from the it should be the same, yeah. The composition of Y1 and XD should be it should be the same. Oh yeah, this one Y1, yeah, which is for example 0.95. This is also 0.95 because so see, from if it goes to here, XD equal to Y1. Okay, so this graph Y equal to X show you that the composition of Y, you read it here, yeah, equal to Y1, because there's nothing here, yeah, only there is no equilibrium, only cooling down. Okay, maybe if I put some number, for example, this is 0.9, you go to that way, and then you go to here, you also get 0.9. Okay, so get it, everyone? Because there's nothing here, there's no equilibrium here. So if you got a 0.9, then also you got 0.9 here. Okay, okay, the next one. Okay, so the Y1 is actually there's nothing here, yeah. The Y1 is actually is also the same, came from the stage 1. Okay, so it came from the stage 1, and it is in equilibrium with X1, isn't it? Okay, yeah, it is equilibrium with X1. So when you trace it back into the graph, your point is gonna be this one. This is a point. Is it the orange one? That is an equilibrium. Okay. So this H1, so this point tell you a pairs between X1 and Y1. Okay. Who else? Kevin, can you do annotation? Can you tell me what is the composition of X1 in the graph? How to read the composition of X1 in the graph? You can just go down there. Okay, Kevin? And then you can read your X1. Yeah, that's good. Good. Yeah, so this is how you write, how to read the X1. Remember, later on you have to read them, yeah? Misalnya 0,8 gitu ya, for example, ya. You need to read them. You need to read them in the millimeter block. What's now my question again, Kevin? What is the composition of the vapor Y1? You can draw it again, Kevin. How to read the composition of Y1? Good. Okay, so in one point, this one point on this curve is tell you about the composition of equilibrium between y1 and x1, y1 and x1. Okay, sometimes your friends also kakak tingkat ya will say, oh lihat aja segitiganya gitu. It's not segitiga ya, not the triangle that we're looking at, but we're looking at the points on the equilibrium. Okay, everyone? Yeah. Okay. Thank you, Kevin. Gamma, are you there?
Yes, ma'am.
Yeah. Okay, Gamma. Now, Gamma, now I know the x1 because Kevin has tell me the x1 here. Thank you, Kevin, to get it. Now I want to know the composition of y2. Which line that I should should I use? Equilibrium curve or operating line?
The equilibrium curve.
Nope. It is operating line because now I want to know the correlation this one. Yeah. Remember, correlation the horizontally yang mendatar ya between yn plus 1 with xn ya. N-nya berbeda look ya. Jadi kalau 2 sama 1, 3 sama 2, 4 sama 3 ya. We use operating line. With operating line is the green one. Yeah, if you go back, maybe go back here, see? Yeah, operating line between yn plus 1 with x1, xn. Okay, Gamma, let's go back. So which one that I use to get the x1 to y2?
Use the green one. So
Yeah,
you go
use the green
across.
one. Okay, so this is the coordinate for x1. So I'm gonna go down here and then stop it here. Okay, so this is gonna be like Gamma said that it is on the green line here. So this is my points that represent the operating line. Okay, Gamma, can you read which one is the mole fraction of vapor? Why? How to read this one, the point? Maybe you want to draw?
Mole fraction of vapor.
Yeah, mole fraction of vapor in this point. Because I want to have mole fraction of vapor. You want to read it here, yeah? Yeah, that's good. Thank you, Gamma. Yeah, that's excellent. You want to read it here. Yeah, that's good. So I can see y2. Excellent, yeah? So that means, yeah, good. I have y2 now, yeah? So now I know from y1, I can calculate x1 and I can calculate y2. Now the next step goes to the y2. So, so how to calculate the x2? Fatia. I know y2. How to calculate x2? Fatia, can you draw? Where is x2? Hello? Fatia, are you there? Or Helena again, maybe? How to calculate, how to know the composition of x2? Hello? Hello? Can you hear anyone?
Yes, ma'am.
Okay. Who are you? Well,
This is Dhamma.
oh, Dama. Okay. Okay, Dama. Dama, can you read which one is x2?
Is it where we drag down the line to x2, ma'am?
Okay, yeah, that's right, Dama. Where's mine? Okay. Yeah, this one, yeah, Dama, yeah. Okay, good. So basically, you with these lines, with the equilibrium curve and operating line, you basically can calculate all of the composition for the liquid, also for the vapor in trace, yeah. And then when to stop? That's the questions, yeah. So when is the stop? If you remember the previous slides, you remember that that we have to stop. So I can put it back to here. Yeah, this is actually how to see there. Okay. So this is also the same. If you want to see the trace stage at number 3, you read it here. We're gonna stop it when it goes to the feed stages. Yeah. So then we have to the next step is we have to calculate the feed stages. So if we go back here, okay, yeah. So the calculation of equilibrium enriching stages. One equilibrium is to calculate the composition of X with one operating line and the equilibrium correlation. Okay, the lower composition of enriching stage, tahap yang paling bawah ya buat tahap enriching, is stage where the feed. So then we have to, the next part is to understand where is the feed is, yeah, where is the feed, yeah. The stage composition is not similar with the feed composition, yeah, it's not a different, and we have to calculate it first. Okay, so everyone, going back to here, this is very, very important. This is also, again, it's gonna be always in the exam. So in the exam, we always calculate, okay, this is the distillate that we want, construct the number of enriching stages. So you should be able to construct enriching stages by first drawing the equilibrium curve, and the second one placing the equilibrium, the operating line, and then you start to construct those, this one, yeah. Okay, all right. Maybe you want to have a little bit of stretches, and then let's go to the next slides, yeah. Okay, I need to there. Okay, put it. Okay, so this is the end of the module 2, and then let's go to the module 3, segment 3. Okay. Right. Give me 1 second. Okay, good. Okay, so everyone, I have actually I have 4 school children, yeah, at home. So sorry sometimes. So some of them very, very small, second year elementary school, for 4th year elementary school, yeah. So those two, maybe the second one is sometimes they have the schedule for Google Meet, yeah, jam 10 Google Meet. So sometimes when I have to teach at this point, yeah, I always miss it, yeah. Kelas 2, yeah. So still second year in the elementary school. Sometimes she's just busy playing and doesn't know about the Google Meet. I need to check the assignments, yeah. Right. Okay. Yeah, anyway, some intermezzo. So for school children, it is very difficult to learn by themselves, especially so they need to be again mentored by the parents, of course, yeah. Perkalian pembagian. And for you, I don't know about you, yeah. Can you do it everything by yourself with the PJJ, pembelajaran daring? How about you?
Do you mean by doing by yourself, ma'am? What do you
Yeah.
mean by doing by ourselves?
Just watching, and then after that you understand, okay, I can do all the assignment by myself. Can you do that? Or what is your strategy? Or you have to talk with your friends and then have another Google Meet and Zoom with your friends?
I think it's because we're already university students, we adapt faster, and
Okay.
yeah, it's either talking to friends or just solitary studying.
Okay, so if you seeing again the recording, you can start to understand by yourself as well, yeah.
That's usually how we do it, ma'am.
Okay, good. So okay, that is good. Yeah, at least I hope you yeah. So just let me know if you think you're getting lost in somewhere, and then we can have more tutorials. Yeah. Usually I have even I'm the instructor, I'm the lecturer. Sometimes we have another additional tutorial. Prior the exam, because it's very important, yeah. Because in my case, when I was even in Teknologi, yeah, I always ask my friends. I always ask my friend who is more clever, and then ask them to teach me. Yeah, if I don't know anything, yeah, if I don't know ini gimana jalannya or something, yeah. Use all your resource. If you can ask your friends, if you can have a maybe group session, yeah. If you have gang, yeah. If you have, do you have gang? Gang atau apa? A group of friends, yeah. Try the best yourself, yeah. Because I don't know, because usually in the class, I always write a lot in the whiteboard, and then sometimes I give all of the maybe a dummy of graph, yeah, to you all in the international class, because only maybe a few of them, yeah, about 15 or 14, and then I can go around you and then check the progress for you one by one. But now I can't do that. So if you think you're getting lost a little bit, or yeah, just let me know, or so we can discuss together. Okay. All right, just a little bit intermezzo, because yeah, for children it is really basic foundations, and but for you as well, it's gonna be your basic thinking, yeah, systematic thinking for you as an engineer. Even if after you finish your study, you don't want to be a chemical engineer, yeah. I want to go to energy management, for example. I want to go to bank. I want to go to McKinsey. I want to go to management, for example. But this systematic thinking that we give to you in chemical engineering is gonna be really basic thinking, yeah. One of my students 2012, ya, yesterday I saw his photo getting master in management in Michigan. I think Emma also go to Michigan, yeah. But that means after you finish the bachelor degree in chemical engineering, you have a number of opportunity, yeah. If you want to go, for example, if you want to do master, if you want to do anything, is like countless, yeah, a lot of opportunity. But so that's thing, we have to adapt with the online learning. And then let me know if you think you're getting lost, and then have more explanation. All right. Okay. So now, so the first one. So we finished the operating line, the enriching. So let's go back now. Let's go to the stripping line. Yeah, the stripping section. So if you look at the stripping section, this one here, the stripping section fractionation column here. Looks similar, yeah. It's quite looks similar, but of course the amount of vapor and the amount of liquid, of course, gonna be changed, because you got the feed somewhere in. Okay, so it's gonna change. Okay, so we're gonna write L dash for the liquid, and we're gonna write V dash for the vapor. Okay, this also quite similar. So the following is the scheme of the stripping section of the fractionation column. The stripping section has M equilibrium stage outside the reboiler, but actually this is actually one stage. Okay, yeah, this is stage 1. So for stripping, we gonna count it from the bottom, yeah. Tray paling bawah, the bottom one is the stripping section, yeah, the number 1. So we're gonna count it from the bottom. This one also, which one? Number 2, number 3, number 4, and up to M. Okay, the reboiler, yeah, the reboiler vaporize some liquid from the bottom, vaporize some liquid from the bottom part of the column and then recycle back to the column as the stripping vapor, while the other, all the liquid is drawn as the bottom. So, what do you think about this one? Is this an equilibrium or not? Equilibrium stage or not? There is vapor and liquid. B is a liquid, yeah. There is a vapor and a liquid. And when it's lift, it should be in equilibrium. So this is actually, for a boiler, is one stage of equilibrium. Yeah. But when we calculate the stages in the fractionation, we count number 1 is from here. Okay, so for example, I calculate the stripping section. For example, I have enriching is 9 stages. Okay, I have stripping is for example 8 stages. Okay, so the total equilibrium stages in the tray is 17. Yeah, but then we add reboiler 1, so the total amount equilibrium stages in the system distillation column is gonna be 18. Right? Okay, up to here, any questions? No, not yet. Okay, let's just continue. Okay, so now go back again the mass balance of the stripping section of the fractionation column. Again, it's quite similar with the previous one, so I'm gonna be a little bit faster. Here we have LM goes inside there, and the one that goes out is VM and also B. Yeah, so VM plus B. Okay, the component A mass balance is X M plus 1 multiplied with LM, that one, and then plus equal to YM LM YM VM plus XB divided by B. So it's basically the same with the previous one but different envelope. Okay, everyone, yeah? So from here, from those two equations, and we will get this one, the operating line of the stripping section, minus, or I think it should be plus, yeah. Let's go back. Oh, minus, yeah. Oh yeah, betul. Yeah, it's minus. Let's go. Oh yeah, the XB, yeah, for there. Okay. This one, yeah, minus. Okay, and after that, L over V again is better if we change it with the reflux ratio. But then, but the reflux ratio now is not. But we don't know the reflux ratio, yeah, because it's reflux ratio is in the operating in the enriching one, yeah, in the top side. So then with the constant molar overflow, we also can get the correlation of YM and XM plus 1 here. This one, yeah. So sorry, we can't change the L and V, yeah, because it's different. This one is different, right? So that now look at in here. Let's see the mass balance in the reboiler. Let's check also the mass balance in the reboiler, and then L1 equal to V0, yeah, plus B, or L equal to V plus B, yeah, and also L dash minus B equal to V, yeah. So the operating line become this one. So this is the operating line of a stripping section. It's also a linear equation, and it goes to points XB and XB. Okay, so it is, so that means if we write xm as the for example yeah, it goes to, if the xm is we calculate with xb, yeah, and also this also the lm will also become xb. Okay, so up to here, this also from here it gonna be looks like this. So basically for the stripping section, we don't know what is L, V, and XB, but basically first it passed the XB over here. So XB usually small, yeah, for example 0.05 gitu ya, contoh ya, very small, so maybe somewhere around here. So it passed XB and XB, and then the feed, or sorry, the gradient is called L dash and V dash. Okay, and this is one is called the enriching section. This one is the stripping section. Yeah, so the intersection between the stripping line and also the enriching line is called the, this is where the feed come in. Okay, so again, the stripping section or the operating line of the XY diagram is through XB, this one. Okay, the slope is L dash divided by V dash, this one. And then it gonna intersect with the top operating line with the green one, and the cross line with the top the operating line over here is when is the feed comes in. Okay, so that now the next step now is how to calculate the feed. Yeah, now okay, so we have to know what is the impact of the feed. This is a little bit tricky. So what time we have? Okay, about 20 minutes. Yeah. Okay, the feed, the schematic mass balance. This is the schematic mass balance. Yeah, this is the feed come in. If the feed is all vapor, so all of the vapors will go to here. Okay, if the feed is all liquid, all of them is gonna be go to the liquid there, to the stripping one. Okay, if the feed is mixture between a vapor and liquid, so the vapor will go to the vapor and the liquid will go to the liquid. Okay, so back again, we have to call, if we can, so how to get the operating line. So usually we because we don't know how to, so okay, let's read how to get the number of equilibrium stages. If we can draw the operating line for enriching and stripping section, thus we can calculate the number of equilibrium stages. Okay, okay, Dhamma, can you get XD from the question, from the problem? Usually you can get XD, yeah, from the problem, yeah?
I think so.
Yeah, usually it always be stated in the problem, okay? When we designing a distillation column, always they will always state it, the distillation column, because how to design, yeah, if you don't know the outcome. Okay, the reflux ratio, can you determine it? It should be able in the it should be stated in the problem, yeah, also, yeah. Then you can construct the green one. Okay, yeah. ZF. Okay, so the next one is and also ZF is the feed composition. Kevin, do we know the feed composition?
The feed composition is the intersection, right? ZF.
Yeah. Do we know feed composition in the problem? Should be, yeah.
Yes, I think
Yeah.
so.
Oh yeah, of course, because how to design distillation column if we don't know the feed? Okay, so we know the ZF. if we know the stripping column, yeah, if we know the stripping operating line, then we can okay, and then like this, for example, and then we know also the stages, yeah, somewhere here. But so if we know the L over V, L dash and V dash, we can construct the stripping column, and then we can make equilibrium. So this is equilibrium stage 1, stage 2, stage 3, stage 4, and stage 5, which is the feed, for example, this case. And then we have the stripping column, stage 6, stage 7, and stage 8. Yeah, goes a little bit behind XB is fine, ya. Yang nggak boleh ya adalah sebelum XB udah turun. Ya, if you stop around here before the XB, you have to add one more stages. Ya, sisa harus lebih kurang, nggak boleh masih kelebihan gitu ya. But however, we don't know the value of L dash and V dash, ya. We don't know this one. Okay, we don't know this line, so we can't be able to determine the stage number. Maybe how about if because we don't know, yeah. Maybe I can put it there. It can be I don't know, yeah. So maybe this one, it can be like that. I don't know. So the fifth stage gonna go that way. It can be that one. It can be that one. We don't know, yeah. So what can we do? We have to find another way to obtain the intersection points. Yeah, we have to find another way how to find intersection point. So now the next stage, what we have to do is to find the intersection point from the feed one. Let's go back to the fourth. Okay, make it bigger. Okay, right. So in the stage where the feeds come in, yeah, they will have the mass flow. They also will have the energy with them, yeah. Or what is the energy? It's the enthalpy, yeah. They will have the enthalpy. Okay, so we have to now let's see the energy balance. Wait, just a little bit. Just give me 1 second, yeah. Okay, let's go back, yeah. Okay, so stage where the feed in here, so F HF, let's check the balance. So F multiply with HF, this is the input, yeah. And then the one that is in, also there is a vapor, V dash from the stripping, yeah, V dash from the stripping, multiply with its enthalpy. And also L, again L with the liquid also inside, yeah. So let's look at the energy balance. That's equal to the one that goes out over here and also the one that goes out over here. Okay, so this is the energy balance, and if it's ideal, the enthalpy of vapor, because this is quite similar temperature, yeah, not much, then it's equal, yeah, between the HV and also here, and also the enthalpy of those liquids. Okay, and then we're gonna define the enthalpy with Q, or a feed thermal condition. It's defined with dose enthalpy of vapor minus enthalpy of the feed divided by the enthalpy of the composition in the full vapor minus enthalpy of the liquid. Okay, so that means here, if feed is saturated vapor, yeah, so Q become HV minus if the saturated vapor, so the feed enthalpy should be equal to vapor, yeah, isn't it? Vapor divided by enthalpy of vapor minus enthalpy of liquid. HV minus HV equal to 0. So that means if there is saturated vapor, the Q is equal to 1. Yeah. How about if the feed is saturated liquid? Yeah. Q equal to HV minus HL divided by HV minus HL. So what is the Q? Can you help me? Similar. So that's equal to
1, Bu.
Yeah, good. So that means if Q is 0, it is saturated vapor. If Q is 1, is saturated liquid. If the feed is somewhere between liquid and vapor in two phases, so the Q is between 0 and 1. Okay? If Q is if the feed is superheated vapor, ya, you know superheated vapor tapi lebih jenuh lagi ke atas, ya, superheated vapor, then maybe Q is more less than 1, ya. But if the Q is saturated liquid, maybe subcooled liquid, ya, yang belum kelewat liquid jenuh, lebih dingin lagi, the subcooled liquid, so Q may be more than 1. Okay, so this is one of the parameters that we're gonna use for the feed thermal condition. Yeah, this one. This is what we like to calculate it. Yeah, so Q is the HV minus HF divided by HV by L. So by the calculation again for the feed thermal condition, we know that Q, the saturated liquid, Q equal to 1, while it is saturated vapor, Q is equal to 0. If it is a liquid vapor mixture, it is between 0 and 1, of course. Yeah. And if it is, we call subcooled or undercooled liquid, Q-nya positive, ya, more than 1. While if it is saturated vapor, the Q would be a negative or minus less than 0. Okay, so why we have to calculate the thermal condition? Now that's very interesting. So the engineers try to make a line, yeah, to make a line. Or try to find something in correlation with the graph. Okay. So here, okay. So if the top section enriching operating line is this one, the bottom section is this one. It's basically by looking at those correlation, yeah, the correlation. That first the L minus L in the liquid, yeah, in the liquid that goes to the stripping, minus, so liquid goes to the stripping, minus the liquid from the enriching, put it here, yeah, the liquid goes to the stripping, the liquid goes to the feed tray, minus the liquid goes to the stripping, that is actually the QF, yeah, the thermal F. Remember that because if we Q equal to 1, it is full liquid, so this equal to QF. Okay, another one, if the let's get another one here with the red one. If we have V, yeah, and also this one is V from the stripping, yeah, minus V, that's equal to the vapor, yeah, that's equal to the vapor, or Q minus 1 of the feed, yeah, should be, because it's actually start from V minus V dash equal to feed multiply with my 1 minus Q ya. The fraksi vapor kan, Q itu fraksi liquid ya. Q is the of the liquid. And then so 1 minus Q is the fraction of vapor. So the delta between V and the V dash is this one. But then we just change it, and so V dash minus V equal to Q minus 1F. Yeah. So it's basically from this one, we rearrange them, we combine them together, and divide them with the Q minus 1. So then we have, we call it Q line. Okay. A Q line, this is an equation that shows that the intersection and enriching and stripping section operating line. Okay, this is tell you because you combine them, yeah, between the feet. This one you combine them with this one. Yeah, when you combine them, that becomes this one. So this is equation 1. This is equation 2. If you combine equation 1 and 2, that becomes equation this one, and divide both sides with Q minus 1, that becomes this one. This is called Q line. Yeah. So what is Q line? This Q line like this. This Q line will go through point ZF and ZF. So if we change X with ZF, so the Y become Q divided by Q minus 1 of ZF minus ZF divided by Q minus 1. So this become Q minus 1 Q minus 1 ZF. Okay, so that becomes ZF. So then Y is become ZF. So this 1 point. Yeah. And this one is goes to the intersection. Yeah. And it has a slope. The gradient is this one. Q minus Q divided by Q minus 1. So that means if we know the thermal condition of the feed, we can get this Q line. So once we get the Q line, we can get the intersection with the enriching one. And from this point, we can draw a line to get the stripping line to get the XP. Okay, so here, so if we can draw the Q line, the intersection point now is known, this one. We can draw the bottom stage or the stripping station to the XB, and then we can calculate the number of equilibrium stages. Okay, let's try how to calculate gradient. We need the gradient, yeah. Okay, let's say saturated liquid. Check the slope. Siapa ya? Fatia, are you there? The slope is Q minus 1. Q divided by Q minus 1. So what is the Q in the liquid? Fatia, let's go back. What is the Q in the liquid? Fatia? Or Helena? Who can answer me?
It is 1, ma'am.
Yeah, okay, 1, yeah. Okay, Q is 1. So go back to here. Let's write, yeah. So slope is 1 divided by 1 minus 1. That's equal to?
Undefined, ma'am.
Undefined, good. Yeah. So this is undefined, good. So if you want to get the slope undefined, so it is a vertical one, yeah, a vertical one. Delta y minus delta x sama dengan undefined, yeah. So this is a vertical one. Okay, next, Kevin, how about if it is saturated liquid, saturated vapor? What is the Q?
If it's saturated vapor,
Saturated vapor, yeah. Go back to here, yeah.
0 is
0, yeah.
0 because HV minus HV.
Yeah, good. Yeah, you remember. Okay, 0. Okay, so if it is 0, then what is the slope? 0 minus 1 equal to
0.
0. So this is the slope for saturated vapor. Ya, mendatar, horizontal. Ya, oke. Lagi ya. Who yang apa? Siapa yang belum dipanggil? Dia. Now I have a feed that is combination, of a mixture. 50% liquid, 50% vapor. What is the Q? Q is fraksi cair, ya. So you can say Q is the liquid fraction because when it is saturated liquid, Q is equal to 0. Kalau nggak ada liquidnya, Q-nya 0. So if it is 50% liquid and 50% vapor, what is your Q?
Is it half?
Yeah, that's right. Good. How about the slope? So the slope now actually half, divide by half minus 1. Setengah dibagi setengah minus 1. Sama dengan?
Minus 1.
Minus 1, good. Okay, so minus 1, that means you have to get the delta x is delta y, minus delta x divided by delta y. So maybe around that one. Yeah, maybe this one, yeah. So this is when you have 15% liquid. Okay, you got it? So this is your Q line if it is saturated vapor. This is your Q line if it is saturated liquid. And this one is you have 50% liquid and 50% vapor. Okay, so then you can draw the Q line and then you can draw the bottom stages and then you can calculate the number of equilibrium stages. Right? Almost 11 o'clock, so I think we have to stop. Okay, so and then I'm gonna stop the recording here.